All right, so on the left side, we have a question where we're asked to apply L'Hopital's rule to evaluate a limit of a trigonometric function. And on the right side, we have L'Hopital's rule, which was taken directly from a book called Thomas Calculus by George B. Thomas Jr. And I'll put the link for that book in the description. We did a more in-depth analysis on what L'Hopital's rule is in our last video on how to use L'Hopital's rule to evaluate a limit, part 1. So if you're not familiar with this format here, that's totally okay. Just go back and watch our first video on how to use L'Hopital's rule to evaluate a limit. That said, let's go ahead and get started here with this question. So this question says, use L'Hopital's rule to evaluate the following limit. The limit as x approaches 0 for 1 minus 3 sine of x raised to the power of 2 over x. So the first thing to do when you're asked to apply L'Hopital's rule, or if you suspect that you might have to apply L'Hopital's rule, is to plug in 0 into the function to see if it's in indeterminate form. We're going to go ahead and plug in 0 to our function here. We're going to break this up when evaluating this function. First, we'll start with the base. We'll find that the base, which is the part that the exponent is attached to, is going to equal 1. Next, we'll evaluate the exponent. The exponent portion is going to equal plus or minus infinity. The result is going to be 1 to the power of infinity. This is considered to be indeterminate form. Now that we have confirmed that this is in fact an indeterminate form, I'm going to go ahead and clean this up. And now we're going to look at the function. What to do? We're going to apply something that's often referred to as the log trick. To apply the log trick to our function, we're going to need a formula. So this here is the formula that we're going to apply. Here in our expression, a equals 1 minus 3 sine of x and b equals 2 over x. Now we're going to apply the log trick. Next, we're going to take the natural log on both sides. Let's look at this portion right here. Notice that 2 over x is the same thing as 2 times 1 over x. So that means that we can rewrite this. The reason that we rewrote this is because it lets us see clearly if we have an indeterminate form, like 0 over 0. And this is a lot easier to recognize if it's in fraction form. So now let's check what happens as x approaches 0. I'm going to clean this up a bit. In the numerator, as x approaches 0, the result is 0. Now let's check what happens in the denominator as x approaches 0. In the denominator, as x approaches 0, we're going to be left with 0, because remember, we're just plugging in 0 for x. So that means that the result is 0 over 0, which is still an indeterminate form. So we're going to have to apply L'Hopital's rule a second time. Let's differentiate the numerator and the denominator. So we're looking at the numerator here, and it's a composite function, meaning it's a function within a function, right? So what's the inside function here? Well, the inside function is going to be 1 minus 3 sine of x. So we're going to differentiate the inside function. How do we take the derivative of 1 minus 3 sine of x? Well, we're going to break this up term by term, and we're going to take the derivative of each term that we see present in the function. So how do we take the derivative of 1? Well, 1 is a constant, and there's a rule for taking the derivative of a constant. So here we see that the derivative of a constant is going to be 0. So the derivative of 1 is 0. Next up, we are going to take the derivative of negative 3 sine of x. To take the derivative of negative 3 sine of x, we need to apply the constant multiple rule for derivatives. The constant multiple rule for derivatives says that any constant times a function is equal to the constant times the derivative of that function. So here, our constant is going to be negative 3, and our function is going to be sine of x. That means that we're going to take the derivative of sine of x. Then after we take the derivative of sine of x, we're going to multiply it by negative 3. The derivative of sine of x is always going to be cosine of x. So therefore, the derivative of negative 3 sine of x is going to be negative 3 times cosine of x. This, of course, is just going to be negative 3 cosine of x. This means we are going to combine what we found for the first term with the second term. What we found when we took the derivative of the first term, 1, was 0. So we'll add 0 to what we found for the second term when we took the derivative of negative 3 sine of x, which was negative 3 cosine of x. So our result, negative 3 cosine of x. There's something called the chain rule for logarithms, and I'll write it out. Written in pink is the chain rule for logarithms. Now, if we set 1 minus 3 sine of x equal to u, and its derivative, negative 3 cosine of x, as u of prime, we can now plug this in to the chain rule for logarithms. The derivative for the numerator is going to be negative 3 cosine of x over 1 minus 3 sine of x. Now that we've found the derivative of the numerator, we can move forward by finding the derivative of the denominator. In the denominator, we see that we have x. So how do we take the derivative of x? We can do so by applying the identity rule for derivatives. The identity rule for derivatives says that if you're taking the derivative of a variable, it's just going to be 1. So the derivative of x is just going to be 1. What we'll do now is apply L'Hopital's rule. What we have is the limit as x approaches 0 of negative 3 cosine of x over 1 minus 3 sine of x. What we'll do now is we'll evaluate the limit at 0. We have evaluated it at 0 and we have a result of negative 3. But recall that there was a factor of 2, so we need to put back that constant. After we put back the constant, we get a result of negative 6. What we'll do now is undo the logarithm. The rule is if the natural logarithm of y approaches L, then y approaches Euler's number raised to the power of L. We're going to apply that rule now. then that means the limit as x approaches 0 for y equals Euler's number to the power of -6. And that's our answer.